So yeah, as I announced, there won't be any more tutorials or quizzes. Instead, you will be submitting homeworks and then one problem will be graded. Okay. So now let me start the lecture. The lecture that I posted yesterday, actually I posted it day before yesterday night, but somehow I forgot to do something on YouTube, so it didn't go through. So yesterday morning it should have appeared. Let me quickly summarize what I did during that lecture, the last part at least. So the whole lecture was about pullbacks of differential forms, and the last part was this one. So I had 3 open sets at E, V, and W. In Euclidean spaces of possibly different dimensions. And then I had 2 maps, C1 maps, S and T. And I had omega, a K form in W. Then the claim was that, so if I look at S composed with T, this is a map from C1 map from E to W. And I can pull back the K form on W back to E. So that is what we denote by omega S subscript S composed with T. On the other hand, I can first pull back the K form omega to V and get omega S. So I'll end up with a K form here in the middle. Then I can use T to pull it back to E. That would be omega S, and then you pull it back to E, T. The claim was that these two are equal. And so yeah, the proof was not that difficult. It just reduced to proving, considering a very special type of omega, namely one forms, in fact, something of the form dz. In the proof, I had used coordinates x here, y here, and z here for this. Right. Now, that was just a small thing actually, but essential. But keep in mind that the overall main thing that we are heading for is a kind of change of variable formula for integrals of differential forms. So far, we had been just talking about pullbacks. Now, let's see the main proposition. This will almost immediately give the final result that we are aiming for. So the statement is like this: omega is a K form on an open set E. Phi from D to E, a K surface. And then now this is the part which might be a bit confusing at first, but you'll see why this is introduced. Delta is again a K surface, but so here E is in Rn as usual. Delta is just the identity. Delta of U is equal to U. Then, so let all these things be as they are, what they are defined to be, and then integral of omega on the K surface phi is the same as integral of omega phi. Now notice that, well, phi here, phi is from D to E. So when I pull back omega, I'll get a K form on D. And I mean, that is omega subscript phi. So what do I integrate it on? Well, the way we have set up things, if you have a differential form, we don't say that we integrate it on some set, but rather we integrate it on a K surface. So just to take care of that technicality, I mean, in reality, what I'm doing is I'm just integrating omega phi on D itself. But since integrals of differential forms are defined only for K surfaces, which are maps, not sets, so I just put a delta here. After all, delta is just the identity. So this is the statement. Okay. So once we have this, then the main result follows almost immediately. So let's prove this one first. Now, yeah, okay. So it's just a matter of, let's unravel this notation and see what it is that we really want. The left-hand side is omega on phi. Now, what is this? This is by definition integral over d. Before that, as usual, so I'll have to, every proof involving differential form involves saying that it's enough to prove it for a special class of differential forms. Here too, it is this. So enough to check, enough to prove this for a basic form. Now, since, so this is a very trivial homework. You please do this. The purpose of all these homeworks, none of them involve any, none of them involve any new ideas. It's just a matter of checking whether you understand the definitions and what it is that we are talking about. That's it. So this is also similar, enough to prove this for basic form. So in other words, you assume that it is true for omega of this type. What is true? Of course, the statement being here, this entire proposition is true if omega is of this type. Then assume that, and then you prove it for general omega. General omega will be just a sum of these basic forms. So in effect, what you'll be proving is if it's true for a bunch of differential forms, then it's true for the sum, the previous statement. Okay. So enough to prove it for this. And then now let us see what it is that we want once we have omega of this type. So let's denote as usual the components of phi by phi1, phi n. Remember, phi is going from the a k simplex or a k cube in Rk to Rn. So it will have n components as I've denoted here. Now, what is omega phi? Well, by definition, keep in mind that omega is a basic form. So by definition, omega phi would be A composed with phi of u and then d phi I1 wedge d phi Ik. Okay, so with this in hand, now let us see what. So let's see this left hand side. What this is? Omega over phi. Well, this is by definition integral over d of phi was omega was this. So this is A composed with phi of u, and then the Jacobian term. This is my notation, not in Rudin. Phi subscript I of u, and then du. Yeah, actually here I should have mentioned one thing. When I just write du in this is notation coming from our definition of the Riemann integral in several variables. This is not the differential form stuff. I mean, when you have a function from an open set to R, then we had talked about what df is. This du is not like that. I mean, u is not any function. This is just some symbol which is used when we talked about Riemann integrals in several variables. That's it. In fact, the distinction between when we are dealing with differential forms and when we are just when the du is just a earlier classical symbol is you can make out because when we integrate differential forms, it will be always on k surfaces, while the classical thing occurs when we integrate on sets. In this case, we are integrating on the set D. So at this point, I should mention something which I should have mentioned a long time ago when I introduced differential forms. See, I made a big fuss about when I talked about integrals in several variables. When I introduced that topic, we were very careful in seeing when we could talk about the integral in the first place. If you recall, we first started by integrating continuous functions on cubes, or rather cells, k cells. Then we said that we could actually use this to define integrals on k simplexes as well. Then we also said that we could integrate continuous functions with compact support. So in effect, we have only three cases in which the classical Riemann integral was defined. Continuous functions with compact support on Rn, or integrals of continuous functions on K cells or K simplices. But fortunately, that's good enough because in the here, for instance, this integrand A composed with phi of u, j phi u, this whole thing is, of course, actually, well, it is certainly going to be a continuous function on D. And remember that I said that D is always going to be a K cell or a K simplex. So this makes perfect sense. It's a bit late to say this, but anyway, this makes perfect sense because it fits in with our definition of Riemann integral of functions, continuous functions, whether and it basically it fits into one of those three categories. It's in fact the first two categories, K cells or K simplices. So this is what this omega this thing is, and then the other side is integral of omega, the pullback of omega on delta. Now what is this one? This is again integral over d right. So let me no, let me not. Let me just, instead of omega subscript phi, I just use whatever expression I have here. This thing here. This is A composed with phi this function multiplied by d phi I1, where it's d phi Ik. Oh, actually I should go back. Well, here I have integral over d of something, and on the right hand side I have integral over delta of a differential form. So let me sort of, I mean, if I want to equate the two, I should at least have similar kinds of integrals. So here also I would like to bring a delta into play here. How do I do that? Well, this is easy because actually I should have started with this one as the second one. So let me just write this again. Omega over phi is integral over d A of phi u j phi I u and then du. Now let's make a general observation. So I want to write, instead of integral over d, just like the top one, I want to write this right hand side as integral over delta. So for that, I'll make the following trivial observation. Note that if f is a continuous function, and I define a differential form like this, then integral of f du over d is the same thing as integral of alpha over delta. So this is actually quite important. So this is what this is saying is that here we have a link between the classical Riemann integral and integrals of differential forms in a very trivial way. So after all, I mean, if you look at integral of alpha over delta, what is the, to see this, you just start with the right hand side. This is by definition, alpha was already, where was it? Yeah, alpha was this. This is already in the standard form because one, two, yeah. So this is in RK and this is in a strictly increasing order, the indices. So this is by definition alpha composed with delta over T. And then what would be the Jacobian in this case? Well, delta of U was by definition just, it was just the identity map. So the Jacobian would be 1. So that doesn't occur. So this is just this. Oh, not alpha composed with it. So the coefficient A, F rather. F. And well, yeah. Again, delta of U is U. So F composed with delta is just F itself. So this is F du over T. That's it. So the point is that an integral in the classical sense can be written as an integral of a differential form over a K surface in this simple-minded way, just by taking the K surface to be the trivial K surface, delta of U equal to U, and taking the differential form to be, by the way, notice that the differential form here is a K form, but it's a top dimensional form since we are in D is in Rn, Rk. So using this, whatever we just discussed, I can write this as, this is the same as, well, A composed with phi of U, Jacobian phi of U over delta. And then instead of du, I just put du1 wedge duk. So the reason why, as I said, the reason why we are doing all this is that I want to replace the integral over a set with integral over a K surface, because in order to compare with this one. So I have this, and then I write it like this. Okay. So these two things will be equal if and only if these two will be equal. Notice that both are now integrals over delta. So the integrands should be equal. And well, A composed with phi is the common thing. So that doesn't play any role. So what is important is that this thing here should be equal to the remaining stuff here. Therefore, we are done if this d phi I1 wedge d phi ik, if this is equal to j of phi of I u du1 wedge duk. Now, actually, if you had learned, if you had introduced differential forms in a, as I have been repeatedly saying, the whole theory of differential forms could be introduced through linear algebra. You don't even need to talk about smooth functions. Certainly not. You don't need to talk about integrals. Just starting with vector spaces and multilinear maps, one could have introduced the whole theory of not exactly differential forms, what are called alternating K forms. And then one could have brought in smooth maps, etc. But in that context, this becomes a purely linear algebraic statement actually. Here it's kind of hidden. Derivatives, integrals, linear algebra, everything is mixed up here. So it might appear a bit more not so clear, but in fact, if I had time, I would have mentioned that more general aspect as well. That makes things very clear. Here, I have, yeah, in fact, if I have time, what I'll do is I'll just put up a PDF file just explaining the linear algebra behind this. At any rate, this is the main point here. What this d phi I1, etc., equal to this. If we have this, then we are done. So let's try to prove this part. So keep in mind that this, after all, this is by definition determinant of phi I prime. Again, that was my notation, that phi I of u is phi I1 u phi ik u. Phi I was a map from D to Rk. So, yeah, let A be phi I prime with entries alpha pq. So it's a usual derivative matrix of phi I. So alpha pq will be dq phi ip of u. Here, of course, p and q run between 1 and k. It's a k by k matrix. So the point is, I want to start with this left-hand side here and then somehow end up with the determinant. It should be clear how one can proceed. I mean, after all, we have a expression for d phi I1, d phi I2, etc. as sums of other one forms. And then you just plug in those expressions, you will get a very complicated thing when you simplify this wedge product or exterior product. But at the end of the day, you should just end up with determinant of something times this particular form. So that's what we do. So we just write down d phi I p for any p not d phi I p is d, by definition this is dq phi I p of u and then dup, which with our this new notation alpha, this would be alpha, and this is summation over p, alpha pq and then dup. Oops, not dup, duq. duq. You just plug in. Now let's plug all these expressions. So what we are interested in is, remember we were trying to simplify this, d phi I1 wedge, d phi ik. Well, for each of these d phis, you plug in these expressions here. So for instance, the first one will be summation over alpha 1 q. Now I can't use, so I'll have to use q1, q2, etc. d u q1. So q1 equal to 1 to k wedge, etc. All this. And then use distributivity of addition over wedge products. So we'll get an enormous sum. So summation over q1, q2, etc., qk, alpha 1 q1, alpha k qk. Now, what is the differential form part? du q1, that's a term which occurs with this, and wedge du qk. So these q1, q2, qk, they vary independently of each other. 1 to k, qk is k greater than or equal to 1. Now we have seen terms like this many times, and we know that the crucial property again underlying all this is the anti-commutativity of wedge products of one forms. So one immediate consequence is that if qi equal to qj, the term won't even appear here. It will be this part will be 0. So the upshot is that, so I'll leave it to you as an example. We have done this a couple of times, but it's one of the most crucial things underlying everything involving differential forms. So I'll leave it as a homework for you to check that this expression duq1 duqk, as I just remarked, the moment two indices qi and qj are the same, this thing will be 0. So we just have to worry about when they're all distinct. So in other words, q1, q2, qk will be a permutation of 1 to k. That is the only case to consider. And in that case, this will be that S function that we had introduced when we talked about determinants, which is just the sign of the permutation actually. But you don't need to know that. You can directly prove this. du1 wedge duk. So you can put this in the standard form. And to do that, you will just have to do lots of flips. And the number of flips will be exactly this S. So this is a very important homework. So please do this. We are, as I said, we have used this at least once earlier, but now I'm stating it explicitly. So this is equal to this. By the way, I don't even have to mention that this Q1, Q2 QK are all distinct. If they're not distinct, anyway, this S function will be 0. The way it was defined, it will automatically be 0. The right hand side will be 0 and left hand side will also be 0. So you'll be left anyway. If you want to prove this, you'll be left considering the case when they're all distinct. And then you have to argue that this equation holds. So plugging this back, so this thing here, if you plug it back here, you just get the determinant. Therefore, d phi I1 which d phi ik is equal to summation over alpha 1 q1 alpha k qk du1 duk. Now, yeah, right. So oh, I forgot one crucial thing. I forgot this. Well, where was that? S Q1 QK. Now, what are these Q1, Q2, QK? I really don't. I mean, I can make them in increasing order, but I don't care. I just put them as varying independently, 1 to K. I know that anyway. So I get this. And this du1, etc. This is a common factor for all the terms in the sum. So I can take it out and just get sum over alpha 1 q1 alpha k qk s q1 qk, and then whole thing du1 etc. duk. This by definition is the determinant of A, the matrix A with entries alpha pq, which was j phi of. So you're done. Oh, I forgot this. Multiplied by du1 duk equal to multiplied by du1 duk, which is exactly what we wanted. So this expression here is equal to this expression here. So the point is that when differential forms are almost synonymous with determinants, and it's just a formal way of speaking about determinants. So wherever you have differential forms, determinants are bound to make an appearance, like here, for instance. And why that happens is basically the anti-commutativity of the wedge product. So we are done. I mean, we are done because this equal to this, and if you go back and see, we will get, finally we'll end up getting integral of omega over phi is equal to integral of omega phi over delta. Now we can give a one-line proof of the main theorem. Remember that the main theorem was, I start with a K form on V and a C1 map from E to V, C1, and a K surface in E, then integral of omega Well, if I want to integrate omega, I need a K surface in V, but I have a K surface in E. Of course, I have this C1 map, so I can compose. So this is T composed with phi. This equal to integral of, on the other hand, I can pull back the K form on V to E. So that is omega T and integrate it with respect to the K surface in E, which is phi. So this is what we want. This is a general statement. So let's prove this using the main proposition. So integral of T composed with phi. So to be clear, let's just indicate everything in this thing schematically. So this is phi and D. This is T. Omega lives here. So, right. So this is equal to T composed with phi is a K surface here. T composed with phi is a K surface here. Now, what had we proved in the main proposition? We said that integral of omega over phi is integral of omega phi over delta. Now, let's apply this main proposition not to phi. Here, phi has a different meaning. But instead of phi, you use T composed with phi. Omega is still here in V. So I have T composed with phi. So I'll just get omega T composed with phi over delta. Delta is still the same delta as before. Delta from T to D is the identity map. Delta of U equal to U. Now I use the part about pullbacks and compositions, which I mentioned in the beginning of the lecture. So this is omega T and pullback of that by phi on delta. Now again use the main proposition, but this time instead of omega, applying it to omega, apply it to omega T. Everything else is the same. So I'll get this is the same as omega T and then integral over phi. Just this statement here applied to omega subscript T. And you'll get this. And this equality of these two is what we are looking for. Okay, so all this might seem a bit too abstract, but the only way to understand this is hopefully through more examples. But unfortunately, there aren't any examples in Rudin. So in fact, the next set of homework start with oriented simplices and so on, which is the next topic I'm going to do. Well, but before I start that, I should just mention one thing. when proving this, we did not use the classical um, change of variable formula at all. That involved far more work actually, and the assumptions were also much stronger. The t there was supposed to be um, one to one, and the derivative was supposed to be invertible at all points, etc. And moreover, this E and V were supposed to be in this domains, open sets in the same Euclidean space. So it's these two statements are a bit different, the classical one and this one. You can't get the classical one from this, and you can't get this from the classical one either, because to apply the classical change of variable formula, you need very strong assumptions on t. Here t is very general. So the two are, you regard these two as independent of each other. And moreover, even the final form that the formula takes, there's a huge difference. There was, well, of course, in the classical one, there was a Jacobian. Here you don't see any Jacobian explicitly. It's a rather abstract statement about pullbacks, essentially. But the classical change of variable formula is going to make an appearance soon enough. When we talk about orientation, that's going to be the next. So the next thing that we need is this concept of, we already know what simplexes are. The new thing will be something called chains. So we want to, right now we could integrate on a K surface. We want to expand the class of things on which we can integrate a bit more in a very, what can I say, a very somewhat abstract way again. So let me tell you what this is all about. So first, let me define what an affine map between two vector spaces is. So x and y vector spaces. A function from x to y is affine if the map v going to f of v minus f of 0 is linear. In other words, f of v equal to f of 0 plus a linear map. So essentially it's a linear map plus a translation. Linear map translated by a fixed vector. Now, okay. F is determined by f of 0 and f of vk for any basis v1 of x. This is clear enough, right? So see, I know that f of v minus f of 0 is a linear map. So f of v minus f of 0 is determined by what it does. The reasoning behind it is f of v, so what I called a of v. This is linear. Therefore, a is determined by AV1. If I know its action on any basis, I know what A is. So A is determined by these things. But right, A is determined by this. And this is by definition f of v1 minus f of 0, etc. f of vk minus f of 0. Now I'm told that I already know what f of 0 is and f of v1, etc. is. So I know what is A. Once I know what is A, I know f of v as well, because again, I know what f of 0 is. So I just put f of 0 on this side. So that's, it's slightly, this class is slightly more larger than the class of linear maps. Okay, that is one thing. And the next thing is, we already know what let me remind you what the standard Q simplex, standard K simplex in RK. This is the set which we have called QK. This was the set of all summation alpha I EI one to K, such that alpha I is greater than or equal to 0. Actually, I don't have to add less than or equal to 1. That's automatic. And then summation alpha I is less than or equal to 1. So in dimension 2, I'll just get this this is Q2. In dimension 3, I'll get a tetrahedron in the positive quadrant of the XYZ plane, and so on. Of course, in dimension 1, so this is Q3. Q1 would be just the interval 0 to 1. Now I want to, first thing is, let's by the way, I should tell you that from this point on till we reach Stokes' theorem, the concepts and definitions which will be introduced might be a bit hard to follow, but the mathematics behind it will be very simple. I mean, there won't be any subtle calculations or writing down some careful inequalities and so on. That part will not be there. On the other hand, you will see various definitions which may not make immediate sense. So it's a different kind of thing. Compare, for example, when we proved the change of variable formula for in the classical setting, there conceptually it was simple enough, but it was not quite straightforward to prove. We had to do quite a bit of stuff to get that. Here it's not like that. Here it's more of the mathematics is simple, but the definitions may look a bit weird at first. So here's one thing. No, it's not exactly weird. It's just that it might not be clear why we are doing what we are doing. I'll try to explain as best as I can. Let's see how it goes. So now what I want to do is notice that these standard K simplices are actually subsets of Rk. In fact, they're just closures of certain nice open sets. In Rk. But what if I want to talk about, let's say, instead of, according to this, Q2 is a subset of R2. But what if I want to talk about a triangle not in R2, but in R3? A two surface in R3, which is a triangle. I mean, we already have a notion of a two surface in R3, but this is a special class of two surfaces where the image is also going to look like a triangle. The way we defined a two surface or a K surface is just a C1 map. So that might even be a constant. But I want to capture some nice subsets of Rn which look like K simplices, but look like meaning actually they're images of K simplices by very simple maps, linear maps actually. So affine maps. So that is what I'm aiming for here. I want to get hold of very special K surfaces. These are, let P0, P1, Pk belong to, notice the key thing here is now in Rn, not Rk. The oriented, now this word oriented is going to play a very important role. Affine K simplex which we denote. So this is just notation, square brackets, P0, P1, Pk is the K surface in Rn defined by, as I said, so I want to take the standard triangle, for example, and put it in R3, let us say. I want the shape to be still like a triangle. But of course, the side lengths may change, etc. But I want the shape to be like a triangle. How do I do this? The easiest way to do that is, and I notice one thing here, for the standard simplex, one of the vertices is the origin. I want to get rid of that. This triangle can be anywhere. So if I use a linear map, the image is certainly going to look like a triangle. You can check that. You have to define what it means, what a triangle in R3 is. But you can, once you do that, you can check that a linear map will certainly take the standard simplex to a triangle in R3. But if we are just going to stick to linear maps, 0 will go to 0. So you will get some triangle in R3 whose one vertex will be still 0. If I want to get rid of that vertex being 0, the natural thing to consider is an affine map, and that's what we'll do. Next best thing to linear is defined by the affine map. Sigma from Qk to Rn. Sigma of any element of Qk will be of the form alpha I ei 1 to k, and then P0. This is going to be the new vertex corresponding to origin, as we'll soon see. And then here I'll put alpha I Pi minus P0 1 to k. So what is this? What does the picture look like? Well, yeah, before I write the picture, I'll just observe that, note that sigma 0 equals, if I put 0 here, in other words, all the alpha i's will be 0. So the second term won't appear. So I'll get, I'll get P0. And if I take the standard basis EI, EI is just one times EI plus 0 times EJ, J not equal to I. If I were to write it in this form here. So here too, the only term in the right hand side which will survive is alpha I equal to 1. So I'll get Pi minus P0. There's already P0, so I'll just get Pi. So this map, so for example, in k equals 2 and n equals 3, in this case, what it does is in R3, 0 will go to P0, and then Pi minus P0. So this is E1, this is E2. E1 will go to P1. So P1 will be something here. Let us say P1, P2. E1 will go to P1, P2. So in fact, one can check that this triangle will just get mapped to this triangle here with vertices P0, P1, and P2. That's a simple explanation of this. One has to, of course, check that. Depends on, you first have to define a triangle here in R3 and then just check that this triangle goes to this triangle. So I'll stop here, but just before I stop, I'll just mention why this is, why is this affine? Sigma is affine Sigma is affine. Simply, I mean, for the following reason. If we write, define a linear map A from Rk to Rn by AEI equal to Pi minus P0, then sigma of alpha I Pi equal to, well, what was it? By definition, it was this alpha I no, Pi minus P0. This is, as we saw, this was sigma 0 plus alpha I AEI, which I can write as A of summation alpha I sigma of V equal to sigma of 0 plus A V. So we have written it as sigma 0 plus a linear map. By the way, this from going from here to here, I said that you define a linear map like this. Define a linear map by AEI equal to this. So obviously that means that any linear combination of the EIs will be taken to the corresponding linear combination of Pi minus P0. That's how I got from here to here. So then I'm done. And also another thing is that if one wants to be very precise, here I said defined by the affine map from domain equal to this to this. It's not strictly, it doesn't sort of tie in with definition of an affine map, because affine maps are from between two vector spaces. So the domain should be a full vector space, not a subset. So here it says not from Rk to Rn. It is from here to here. I'm defining it like this. Obviously, for the statement to make sense, I make the same definition here, but I no longer put the condition that alpha I greater than or equal to 0 and sigma alpha I less than or equal to 1. I make this definition for all alpha I in R. Okay. Then it becomes a legitimate linear affine map. But our interest is only in what it does to QK. So I'll stop here. And then again on Friday, I'll resume at this point. Okay. So shall we end?
Sir, one small doubt.
Yeah.
We are calling here oriented affine, but
Yes.
in some of this one we are seeing like a translation motion, but there how it is oriented, which parameter is
I'll come to that. I'll come to see the orientation comes from the fact that this part. It's important that this E1, E2, En, Ek is taken as the standard. We haven't said what orientation actually means, but let's say this specific order of the standard basis is in some sense the right order. So it's the positively oriented is the technical term. You basically basis in ordered basis, not just as a set. So as an ordered n tuple, this is said, if you take this as the reference, then this new triangle that we get here also has an orientation in the sense that this P0 and then P0 for this P0 comes first, P1 comes second, P2 comes third. So it's not just a triangle here. It's a triangle with a sense of which vertex comes first. So in that sense, it's oriented. You can put an arrow, for instance, P0. If you want to draw edges, you can put arrows like this. Okay, so P0 comes first, P1 comes second, P2 comes third. But, right. So, in fact, in the next class, I'm going to elaborate on this oriented part. That is going to play a crucial role. And again, that will come down to this question of, surprisingly, it will come down to a question about determinants again, the oriented stuff. So for now, forget the oriented, just try to understand what this, the other stuff, namely, given k plus 1 points in Rn, I have a well-defined notion of I have a very specific k surface associated to those, which is essentially putting the k simplex with vertices at those points. Now here I've left something unsaid here actually. I didn't require that these points are linearly independent. For example, they can all be the same. P0, P1 equal to P1 equal to Pk. If that happens, obviously you'll just get the constant map, which is not exactly what we want. I mean, if you are looking for exact images of triangles, but we have to allow for those things, degeneracies. Or if only two of them are linearly independent, the image will just turn out to be a portion of a line segment. Even if you start with a k simplex, the image will be that. So all these things are allowed in this definition.
Okay.
Okay. Yeah. Okay. So we'll stop here. Unless anyone has any more questions. Yeah. By the way, as I said, this part is going to be somewhat abstract. So you feel free to ask questions. This will definitely need lots of clarifications along the way, what I'm about to do. It's not just a matter of checking details here. There are hardly, as you can see, there are no computations being done. It's more a question of understanding just concepts. So anyway, you go over this, huh? Yeah.
Yeah. Do we have a date for the end sem?
No, not yet. Have others started fixing dates?
Yes.
But I was not even we didn't even get an email about the INSEM week actually.
Right. So I think there was actually an email sent out to the general
Ah,
all students or something
ah.
about. Uh-huh.
And what was this? So I think the institute has not fixed the dates, is it?
They have actually given some sort of an advice timetable. Okay, we would like you to follow something similar to this, but if you don't want to do that, that's your choice. That's something like that. There was an email. Just let me check.
Yeah, just forward it to me, please.
I'll do that, sir.
Yeah, okay.
Right.
Okay, we'll end here then. Okay, bye.
Bye, sir.